So in the last video, we set up our analysis of this circuit, circuit with a resistor in it and an inductor in it. Let's remember how this worked. We chose a direction for the current. That was an arbitrary choice. It was a sensible choice, but it was arbitrary. If I had made the other choice, at the end of the day, I'd have a solution that will be have the opposite sign. And what's new in this case as compared to what we did before when we only had R's and C's, what's new in this case is that in this circuit now there are two sources of electromotive force. There's the battery. The battery has in it some chemical reactions going on which are giving an electromotive force, creating a higher voltage there than there. But now there's a new source of electromotive force, and that's the inductor. Where does that electromotive force come from? There's no battery hiding inside here. No chemical reactions happening in here. No solar cell. No battery. Instead, the electromotive force in this circuit element, in the inductor, comes from Faraday's law. And the way to think about that is that, what does Faraday's law say? It says that an inductor like this resists changes to the current flowing through it. So if there's a steady, constant, unchanging current flowing through here, there's no EMF between the points A and B. But if the current, let's say the current is going this way, and let's say the current is increasing, then there will be an EMF that acts to fight against the change. That's the essence of Faraday's law. And that fighting against the change aspect was this minus sign. It's the fact that when we walked our way around the circuit, we got minus L di dt when we traversed this circuit element in the direction of the current. The physics of that is Faraday's law. In fact, it's the Lenz's law sign in Faraday's law. And what that means is that if I have a current flowing this way, and the current is increasing, then this is going to fight against this battery. So if the battery is trying to push the current this way, this is going to try and resist the increase in the current. And that's why we get a minus sign. That's why we get something that's non-zero only when the current is changing. So now we're going to solve the equation. How do we solve the equation? Well, I'm going to rewrite it as an equation for di dt. And I'm going to rewrite it as follows. Instead of writing 1 over L, I'm going to write R over L. And then what I have in this parentheses is I minus epsilon over R. And if you stare at this equation, it should be very, very familiar. This is, at the math level, it's the same equation that we solved when we had a circuit with a capacitor in it. Let's walk through what the differences are. There's no differences at the math level. At the physics level, there are very important differences. First important difference is that this is an equation for I. This is di dt. In the capacitor case, we had an equation for dq dt. But if you go back and look at the equation that we got for a capacitor, dq dt was equal to minus a constant times q minus some other constant. The values of the constants are different, and the variable has changed from q to I. But the math equation is the same. So we're going to just write down the answer in a second based on what we did to solve this equation before. So when this was a dq dt equation for a capacitor, was dq dt, there was q there, and this was c times epsilon, so the constant was different. And this constant out front, instead of being r over L, was 1 over rc. So the constants have changed, and the variable has changed. But the math is the same, so I can just write down the answer. In fact, I can graph the answer first. The answer will look as follows. If I plot I versus time, I'll use this color for I, as I did before, I'm going to get a curve that looks like the answer that we got for Q versus T previously. So same physical problem as before, except now with an inductor instead of a capacitor. I close the switch. There we go. I close the switch. At the moment I close the switch, at that moment, no current is flowing. Previously, when we had a capacitor, what we said was at the moment we close the switch, no charge on the capacitor, no electric field energy in it yet. But now current is going to start flowing through it. That was the story before. So the Q started from 0 and rose. Now in this case, I close the switch. At the moment I close the switch, there's no current flowing through the inductor, no magnetic field energy stored in the inductor, and that I is going to start to increase. Now, does the I just jump from 0 to big non-zero value? No way. That would be an enormous change in I. That would give you an enormous back EMF. And the biggest possible back voltage you can get across this EMF is the epsilon from the battery. It can't be bigger than that. Another way of thinking about this circuit is to say, well, this battery has an EMF, the voltage goes up by epsilon, and then as you walk your way around, you have to come back down by epsilon in order to get back to where you started over here. So you have to come down by epsilon and going over these two circuit elements. And I is going this way. You're going to drop by IR here. So when you go across this, you have to drop by whatever the remaining drop is. And whatever that remaining drop is, if IR is really, really small, that remaining drop is going to be epsilon. But there's no way that that drop could be bigger than epsilon. And so that tells me that I can't have a situation. Remember that with a capacitor, what we did before, when we closed the switch, the current jumped up. That can't happen here. So there's an enormous physical difference between how capacitors and inductors behave. When you close the switch on a capacitor, the current just started to flow initially as if the capacitor wasn't even there. The current when you close the switch was instantly non-zero and significant. Not here. Here, the current starts to increase, but as it starts to increase, the back EMF fights back. And the result is that when I plot the solution, I get a curve which looks like this. And it rises initially linearly and then flattens out, and it asymptotes to value epsilon over R right here. And there is a characteristic time in this solution, and it's the characteristic time at which the current has risen to 0.63 of epsilon over R. Same as what we had before, except all of this was for Q's before. And this characteristic time, tau, where did tau come from in the circuit before? It came from this constant out front. It was RC before, and the constant out front was 1 over RC. So this time, this tau is going to be L over R. So let's now write the solution as an equation. So the solution to this differential equation, applying the same math as before, the solution to this differential equation is epsilon over R times 1 minus e to the minus t over tau, where tau is equal to L over R. And to get comfortable with this, you can do one of two things. Go back and watch the video about solving the equation for a capacitor in a circuit again. And notice that it's the same math, except here we have I's and there we had Q's, and the constants have changed. Or just take this solution and plug it back into this differential equation. So take this I of t, differentiate it, see what you get on the left-hand side. Take this I of t, subtract epsilon over R, that's going to get rid of the one term here, multiply by minus R over L, see what you get on the right-hand side, and just make sure for yourself that this really is a solution of this differential equation, which it is. Now let's come back to the physics. So what happens here is that I close the switch, the current is initially 0. With a capacitor, the current jumped up, but here the current this time is behaving like the charge did last time. Remember that with the capacitor, the charge was initially 0, and then the charge rose on the capacitor rose linearly. This time, the current is initially 0, and the current starts to rise, but that induces a back EMF, and the result is that the current rises only linearly. It doesn't jump up. So what's this initial rise in the current? Well, what's happening is that initially, when the current is really tiny, the voltage drop across the resistor is very small. It's IR, but I is really tiny. So the back EMF here is going to be equal to this epsilon, the epsilon from the battery. And so the di dt, so I'm neglecting this term in the equation, and the di dt is going to be epsilon over L. So the slope here, the di dt, is epsilon over L. Okay, now current starts flowing. You know, di dt is positive. Current is increasing. The current's rising. What's changing? Well, what's changing is that as the current is rising, now you get more and more voltage drop across the resistor. I is increasing, so the voltage drop across the resistor, IR, you can't forget about it anymore. This IR is increasing. If the voltage drop across this piece of the circuit is increasing, then that means the voltage drop across this piece of the circuit has to be getting less. For that, what that means is that the back EMF has to be getting less. And that means that the di dt has to be getting less, which means that I has to be flattening out. So the physical intuition is that previously with the capacitor, I had a bucket for charge and I was filling it up. And it reached a maximum value, which was determined by the capacitance of the capacitor and the voltage you had available. And then you were done. Your bucket was full. This, by analogy, instead of a bucket for charge, is more like a bucket for current. Okay? You close the switch, the current starts to rise, but as you're now filling your inductor with magnetic field energy. It's really better to think of it as a bucket for magnetic field energy, and you're starting to fill your bucket up. And you see from the equation that when I has risen to epsilon over R, di dt won't be changing anymore. So when I has risen all the way up to epsilon over R, the current's not changing anymore. That means you filled your bucket up with the most magnetic field energy you can put in there, and given whatever the strength of your battery is. And once you are at that point, what's happening is that I have an I which is epsilon over R. That means the entire voltage drop in the circuit, the voltage rise is from the battery, the entire voltage drop is from the resistor. No voltage drop here, that means the current's not changing anymore. So you filled this up to the most magnetic field energy you can store in the inductor, that you're not adding any more magnetic field energy. That means the current is not changing. If the current is not changing, there's no back EMF. If there's no back EMF, the entire voltage drop has to be across the resistor, and the whole story hangs together. So to summarize, with a capacitor, when you close the switch like this, the charge starts out 0, rises linearly, and plateaus when you have filled your capacitor with electric field energy. Here, you close the switch, the current starts rising linearly as you are starting to fill your inductor with magnetic field energy, and then the rise in the current plateaus when you have got the maximum amount of magnetic field energy you can put into that inductor given the power of your battery. But from a math point of view, it's the same math as before, just relabeling symbols. But from a physics point of view, the physics is in fact quite different. Here, the important physics comes from Faraday's law. Previously, the important physics just came from Coulomb's law, from electrostatic repulsion. What we're going to do next, in the next video, is we're going to focus a little bit more on this time constant, tau, and make sure that we understand everything we can about where it comes from.